Our next award is the Arden Bement Jr. Award, which was established in 2015 by Distinguished Professor Emeritus Arden Bement and his wife, Mrs. Louise Bement, to recognize a Purdue faculty member for recent outstanding accomplishments in pure and applied sciences and engineering. Professor Bement achieved international recognition as Director of the National Science Foundation and Director of the National Institutes of Standards and Technology. He received a doctoral degree in metallurgical engineering, as well as 7 honorary degrees in science and engineering from universities in the U.S. and abroad. He has had a long and distinguished career with Purdue, serving as the Basil S. Turner Distinguished Professor of Electroceramics, the David A. Ross Distinguished Professor of Nuclear Engineering, Chief Global Affairs Officer, and inaugural Director of the Global Policy Research Institute. This year's recipient of the Bement Award is Jay Gore, the Riley University Chair and Professor of Mechanical Engineering, who is being recognized for his highly significant and impactful contributions to big data, artificial neural networks, machine learning, and artificial intelligence in physics-based models of energy. He was nominated by Professor Lucht. I'm pleased to welcome Jay Gore to receive this distinguished award and to share his lecture entitled Big Data, Artificial Neural Networks, Machine Learning, and Artificial Intelligence.
Thank you so much. Thank you. Thank you, ma'am. I got it. Good afternoon. I'm here with great memories of Arden Bement, who welcomed me the first time I received the Riley Chair Professorship at Purdue University. I remember his words from that time, as well as his words from last week. Arden lives in Ohio, but is a great Boilermaker who keeps in touch with us. I will talk with you, I'll share with you some of the thoughts that we have gathered, some of the education we have received from big data, machine learning, and I will use the phrase artificial intelligence with some caution. But I'll emphasize that all of these are meant to keep us safe as human beings. And safety is important to all of us because we are threatened by climate change. Whether it is real or not is not the topic of my discussion today. But what is real is that power plants are going bankrupt and shutting down if they are running on the basis of fossil energy, such as coal-based power plants in North Dakota, about which you will learn, as we learned, starting with 3 to 4 years ago. I will touch on aircraft engine blowouts. Engine blowouts occur because of the combustor inside of the engine not working very well, and we have learned about what are known as lean blowouts. I will discuss how hot surfaces tend to lead to fires, including when batteries overheat, how battery fires occur. And we will talk about fires that occur in very large forests, and finally touch briefly on image recognition utilizing artificial intelligence to protect all of our information. I'll not be able to cover all 4 topics in the time I have, but let's begin with this beautiful photograph, beautiful, including the coal-burning power plant that you see in this picture. This is from North Dakota. It's a real working power plant. And of course, at Purdue, we label the equipment or the system that is called boiler with the letter A. So in this photograph, you see the boiler is here. It's very, very large. The photograph is aerial from some distance. I'm skipping B and C. I'll jump to the furnace exhaust because that will meet your attention, and all of you may be thinking, so exhaust comes out of there, must be really bad, right? I will avoid talking about all of the pollutants, but I will say carbon dioxide that comes out of here is certainly source of global warming. And I will mention to you with the next slide how we can cut it in half with a magical trick. One of the things I want to point out before we move from this slide is that in North Dakota, as in many parts of the world, mining coal is not very difficult. This coal, where the letter F is where the coal mine is, and it is what is called surface mining. And then from F, you quickly move to G, where there is the pulverizer and feeder. These will show up in our discussion later on. Notice that it is a 600 megawatt plant, so this picture shows many large numbers. It shows data from 3,650 days, that is 10 years, 87,600 hours, 5 million minutes, 315 million plus seconds. So these are big data. And just to emphasize how big they are, I have shown the number 1.89216 10 to the power 10 hertz inverse. So inverse of frequency is time, and that is one of the education that we all need to have. These are 10 years worth of data with 10 to the power 10 seconds involved there. What you will find is that this particular power plant and many, many fossil power plants like this one fluctuate. They call it cycling. Cycle their power from full load of 600 megawatt all the way down to 0 when there is shutdown. Frequent shutdowns cost them a lot of money because every time you shut down and you have to restart, that is money essentially wasted. So as we move from here, these were the data that became available to us in a large team, which involved the power plant operator, the National Renewable Energy Cooperatives Association, the US Department of Energy, and Purdue University. This project sort of fell into my group's lap because one of my students remembered me as a thermodynamics teacher, and he said, "Hey, professor, you know thermodynamics, you need to help us." So we said, I don't know if we can help us, but share those big data with us. So this starts with big data. What did we do with the data? We applied the most modern of techniques to it, which involve machine learning, adaptive neural networks, and with caution, artificial intelligence. What happens is we collected these data in the form of power with time as the variable, 10 years worth of data, and they had data separated by 2 seconds. So that made it a lot of data. We collected these and we connected it to important operators, important boilers. We are boiler makers, so we connected it to a superheater, which is super, but it's part of the boiler. That takes saturated steam and makes steam at high temperature at the operating pressure. We couldn't work with all of the data because we had to separate them in good and bad data. So we made time series out of them first. We isolated a validation set, and then we took slices of the time series. So whenever as engineers, we meet a big problem, we know how to solve it. And the only way an engineer can solve a very, very, very big problem is to make it a small problem. And to make it a small problem, we break it into slices. We break it into pieces, and we say, all right, what's the initial condition? How can we make a slice of this particular big data? And so we, in this case, made 14 slices. We had a slice that we called a validation set. We had a training set, and then these were 14 sets that were going to train our adaptive neural network, or ANN model. We used a very simple statistical principle, only the mean square error we validated in terms of why is the mean square different, root mean square of one of these quantities or both of these quantities, why is it different for this validation set versus the 14 other sets, etc. We could do this for many, many, many data sets, and in the field, they would use the phrase hyperparameter tuning. So as a thermodynamics professor, I said, I need to learn these phrases, I need to define them, I need to find a quantitative way to measure them, and more important than that, I need to really use them to make something useful. And that's what we did. If you are interested in the details of how we did it, etc., we can certainly discuss that later. What the time allows me to do is show you many, 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 many data sets. I couldn't even tell you how many data sets went into this, but the big data were certainly with us. And what you're looking at is efficiency versus gross power that the plant was generating, but the efficiency is for the steam generator. So this efficiency could be 100% if all the heat was being utilized by the steam generator to make steam. And very often, 80% of the heat was being used. But many, many times, 40% or more of the heat was being wasted. Another thing we learned is that when the plant was generating a lot more power, a lot of those data are clustered here. Its efficiency was actually decreasing in general, either staying constant or decreasing. We would really like it to increase. And we applied our own analysis called exergy analysis. Some of you may know the definition of exergy. Exergy is part of energy that is useful. Exergy is defined as energy minus surrounding temperature times entropy, the magic word from thermodynamics. And what we found, to our surprise, to our shock, many, many, many times we repeated this calculation, the data don't lie. The data fell into two groups. Some we chose to label them with our proud Boilermaker gold. Others were, I don't have anything against blue. I received 2 degrees from Penn State. But the others were down here, as low as 20% or 25%. That's the factor of 2 I promised you. If you operated up here at 50% exergetic efficiency, you are burning half the fuel. You are reducing the coal to burn to half. You are halving the CO2 emissions. And while halving the CO2 emissions and burning half the coal, you are saving jobs in North Dakota of children who could be the gifted children, some of whose pictures you saw in the previous presentation. We also went into details of what may be the problems, etc. So here's the coal flow rate, and what efficiency is being offered at very high coal flow rates is actually very, very low, whether it's energy efficiency or whether it's exergy efficiency. But all of the boiler gold points lie to 50% or so exergy efficiency, while the blue points, some of them are as low as 13 or 14% exergy efficiency. You could ask me why, and there are many, 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 many reasons that we could go into. However, what I am here to say is that this type of analysis of big data with artificial intelligence, with machine learning, etc., has the potential to save half of your energy. And we are Purdue University, we are boiler makers. All of the electricity we are using here is actually from a pulverized coal power plant that Duke and Purdue run together. If you said to President Chung, who was with us before, that we could save half of the expenditure for that power plant, I think he would take it. He would say, give that person another Bement Award. So this is the paper which is in energy that we published with my co-authors, Navarkar, who works for Microsoft, Hasti, who works for who works at another university, Deneki, who works for Sandia National Lab. Here's the other challenging problem that we will discuss in a little bit of detail with the time we have available. We are all talking about utilizing biofuels as a means of reducing fossil-based fuel usage, including in the aviation sector. Raw biomass comes in many, many different forms. It's processed to make what is called biojet travel. I'll not get into the discussion of whether biofuels are really renewable or not really renewable. My biology colleagues, my botany colleagues are doing a great deal of research in that part, including using lignin-based large biomass where they grow plants in a very rapid manner and make biofuels, etc. I'll leave that part alone, but I would say these biofuels are burnt in the same combustors that the petroleum fuels are burnt, and here you see a very large flame that is burning that fuel, and the blue jets you see are called cross jets that allow the fuel to stabilize and make flames here while the wall remains cool. Occasionally, some of you may have experienced this. I'm really happy that most of us have never experienced this situation where what happens is that there is too much air coming into this combustor, not enough fuel, and leads to what is called a lean blowout or LBO. So we have data for lean blowout that we will be applying our machine learning-based techniques, artificial intelligence-based technique, using ITUP supercomputers as well as DOE supercomputers as well as many supercomputers around the world. So oftentimes, big data processing needs very, very large computers. However, the pilot only has a small computer to work with in his cockpit, and therefore we need to use machine learning and artificial intelligence to reduce the computing burden. I'll not go into the details of the engine in the interest of time, but here's where sits the combustor, and when the flame blows out, there is nothing here, and that combustor, therefore, is not powering the turbine that is powering the compressor. So if the compressor fails, the turbine fails, the pilot doesn't have many choices other than to relight or land. Most of the times they try to relight, but if we were able to utilize machine learning and artificial intelligence as we did here, saying, let's simulate, let's collect a lot of data, let's process the data, let's reduce the dimension of the problem, let's use machine learning and AI-based techniques to develop what is called a convolutional neural network model, CNN, not the television station, but the mathematical model called convolutional neural networks. So applying convolutional neural network, we created a flame that is coming only from the data, only from small amounts of data that the pilot can afford to use in the cockpit and take action against the lean blowout. I kind of mentioned all of this. This is just a summary slide, but what I will mention is that we therefore said computational work could lead to prevention of lean blowout type situations, or there could be sensors that pick up the temperature or concentration of OH radicals that would allow us to do this. Here are the time series of the temperature in the combustor, the OH concentration, the formaldehyde concentration, etc. But what you will see at the bottom is the pressure that the combustor is, the power that the engine is developing, and the warning that the pilot currently could have is just 30 or 40 milliseconds. Time is very, very important, but what I will conclude with is saying that we can detect lean blowout using signals from both OH radical as well as temperature. We have 96% accuracy and 94% recall in the LBO indicator model. And we took data from a engine that was operating, and that data-driven approach and machine learning led us to a paper in Energy and Artificial Intelligence that talks about how to prevent these. There are 3 other groups of students who address 3 other problems, all related to utilization of big data, machine learning, artificial intelligence for keeping us safe. This involved a collaboration, a grant from our Indiana corporation that is a great friend of Purdue, Rolls-Royce North American Technologies. Our co-author is Patrick Sweeney. Patrick was trying to be here. I'm looking around to see Patrick's here in the back. Thank you, Patrick, for taking the time. So that hopefully provided some useful results. I won't go into the detailed discussion of those. Raziel Roncancio comes from Colombia. Our great friend Juan Ernesto is here. Juan Ernesto might remember Raziel. Raziel is very, very happy working for Intel Corporation, where he is working on artificial intelligence and big data. So just by learning about what the students are doing, you might remember that big data, their proper analysis, machine learning, and artificial intelligence, even in the hands of a mechanical engineering professor such as myself, when endowed with endowments such as the Riley Chair, as well as when endowed with great colleagues such as Arden Bement, can achieve some methods of addressing the 5 very, very challenging problems that humanity faces. Thank you so much. I'm happy to take questions. Our vice president has a question, so
Yeah, so
thank you.
I was really interested in your engine blowout because it scares me to death if I'm on the plane with the engine blowout. So your work helped show that. What's the next step in using that big data to really help those pilots with those kind of cases? Does it take a change in software in their cockpit, or what do you need to do to get that so that it doesn't happen when I'm on the plane?
I will take the question more broadly rather than that specific problem by first saying that I fly a lot. I fly all around the world. Sometimes 5 times in a year I have traveled to India. And it is very, very, very safe to travel, triple emphasis. And that is because of corporations like Rolls-Royce that we brought up. That is because of corporations like Boeing, who is a great Purdue friend, and others involved in the aviation business. The way I would address your question is that when we jump in, as mechanical engineers, we were kind of pushed into the field of big data. My request, my answer is that the first thing we should do is educate all of our students that, number 1, big data are not scary. Bad data are very, very scary. Big data are not scary. So how to separate big data from bad data? Statistics helps us. Statistics education, mathematics education is very, very important to separate big data from bad data from good data. Now, if you have good data help us half fuel consumption, reduce emissions by half, etc. Every corporation that I know of in the boardroom are wondering about data science, how much data they have, Do they have really, really, really big data? How could big data be manageable? What type of computers would be needed to utilize those data for profitability, improving profitability, making operations cleaner, making, we were having a conversation in the reception with, I think Dr. Dadalat may be here, and Vaishita is here, and she was mentioning that ethical use of big data is very, very important. So how ethics need to be applied to big data and what types of ethics are being used by possessors of big data is a very, very active question. So my suggestion would be how we could utilize it going forward. Is it to include it in all of our research, to inform all of our faculty, students, that it is not so hard. If Gaur could learn it, you could learn it.